All right, let's pick up on what we did last time. Like I said at the beginning of class, critical values are where the derivative either, equals zero, where it doesn't exist. And there's a last thing that I kind of messed up on Thursday, and I told you that I didn't tell you exactly. But after you do those and find those x values, you're going to plug those x values back into the function and see if it actually produces a value. Okay, those x values are the ones that are our critical values. We did a couple examples last class here, and I think we even did. The thing is, I don't really want to do number 3 because I feel like it's very similar to the quiz. And I feel like it doesn't really help us out. It doesn't give us any more information. I gave you the answers to this one. So if you want to try that on your own, you can. Let's skip over number 3 and just do the last one. Okay. That Jude says was really easy. All right. So in this question, we have the square root of 16 minus x squared. The reason I put this on the packet was because I got a good question about what happens when there's a square root in our equation. And I think that's a really good question to ask. So let's go ahead and figure out first finding the derivative, right? When we find this derivative, what rule am I going to use? Chain rule, right? Looks like we got an inside and an outside function. And let's just go over a little review on how to do this. What's the inside function? 16 minus x squared. And what's the outside function? Yeah, the square root of something, right? Now, I don't really like the square root. I think it looks a little bit bulky. What's another way of saying the square root? Yeah, parentheses to the 1/2 power. Good. So that's usually easier to take the derivative because now we can use the power rule instead of just staring at a square root and not knowing what to do. Okay, chain rule says we're going to take the derivative of the outside. What is the derivative of the outside? So what's the derivative of something to the 1/2 power? Good, 1/2 box to the negative 1/2. If you want to keep this in parentheses, that is a good practice to do too. Okay, and then it says to take this derivative of the outside and multiply it by the derivative of the inside. Okay, what's the derivative of 16 minus x squared?
Negative 2x.
Negative 2x, good. Okay, so that's our entire derivative. Now, a good practice to write the inside the box now. So 16 minus x squared goes on the inside. And in total, it looks like we have, looks like the 2's cancel out. So we've got negative x 16 minus x squared to the negative 1/2. Any way I can simplify that even further?
Negative x over square root of x minus 2.
Good, good. Or not, yeah.
X squared, yeah.
Good. Okay, the negative 1/2 brings that whole box on the bottom, and then the 1/2 power is the square root. So that's why this simplifies in this way. Okay, so we found we found the derivative. Okay, to find critical values, the first thing we want to do is figure out where the derivative equals 0, right? And you can set the entire function equal to 0 and solve for x. What's an easier way to do this though?
Just putting the numerator to 0.
Yeah, just setting the numerator equal to 0. You can do it that way, but just to save a couple steps. And now that I talked too long, I talked as much as writing down the step would be, but that's fine. But the numerator is negative x equals 0. Dividing by negative 1 gives me x equals 0. So it looks like x equals 0 is a candidate for a critical number. Okay. We also have to figure out where the function doesn't exist. Okay. So we need to find out where j prime of x does not exist. Looks like we have both a square root and a denominator going on. Why don't we deal with the denominator first, and then we'll talk about the square root. Okay. I know that this doesn't exist where the denominator equals 0, right? Okay. So the square root of 16 minus x squared is my denominator. Okay, if I want to solve this for x, what should my first step be?
Squaring both sides.
Good, square both sides. So the square and the square root cancel out, so I'm left with 16 minus x squared equals 0 squared, which is 0. Okay, and at this point, it's pretty easy to see how to solve for x. We can subtract 16 on both sides. So negative x squared equals negative 16. Dividing through by the negative gives me x squared equals 16. And taking the square root of both sides, what am I forgetting? Plus or minus, good. So looks like the square root and the square cancel out, so we're left with x equals plus or minus the square root of 16 or 4. Okay, so I have plus or minus 4. That's where the denominator equals 0. Okay, where else does my derivative not exist? Yeah, well, we did the denominator, so that's good, Elliot, but we already did that one. But John says where the inside of the square root is negative, right? So where the inside of the square root is negative. Can't have that, right? So let's just do that. Let's take the inside of the square root and let's set that less than or equal to 0. Okay. All right, well, that would be 16 minus x squared is less than 0. I could go through this and solve for x, figure out where this is less than or equal to 0. But I'm going to tell you, you actually don't have to. Does anyone see why? I'm going to tell you, you already know that any of these x values that you solve for is not going to be a critical number. Yeah, right. If you go back to the question, this square root here is the same square root as the square root in the question, okay? So wherever the inside is less than 0 is not in the domain of my original function, right? So because everything that doesn't work here doesn't work in my function, I already know that if I plugged it into my function, it wouldn't work, okay? So let me write this out, okay? Don't really have a good way of saying this, but any value of x that solves this equation or inequality won't be in the domain of the original function. Okay, do you need the notes from last time, Daniel? Okay, good. Okay, and because of this, I'm not even going to solve it because it's not important to me. I know it's not going to work. Okay, so not even going to care about that. Okay. Usually when we have a square root in our derivative, the original function is also going to have the same square root. So it's not really something that matters too much when we're finding critical values. Okay, so looks like we got 3 candidates for our critical value. We have x equals 0, we have x equals 4, and we also have x equals -4. These aren't our critical values yet because we have to check and see if they actually produce a value in my function. So the way I'm going to check is I'm going to plug x equals 0, -4, and +4 into not the derivative, but the original function, okay? So into the original function, okay? So I'm going to do j of 0. Okay, my original function is the square root of 16 minus x squared. So I'm going to do the square root of 16 minus 0 squared. That's the square root of 16, which is 4. Okay, because I have an actual value, that value exists, I know that this is okay. Okay, we can plug in -4. the square root of 16 minus -4 squared. That gives me the square root of 16 plus, no, minus 16, right? And that's the square root of 0, which is 0. 0 is a valid answer. It doesn't produce an error in my calculator, so that's okay. And j of 4 gives me 16 minus 4 squared, which is also going to be 0, which also works. Okay, so since all these values, when I plug them into my function, give me actual numbers and not error values in our calculator, we have 3 critical values. Are critical values the x values or the y values? Are the critical numbers the x value or the y value? The x value, right? So even though I solved for like 4 and 0 and 0, those aren't my critical values. My critical values are my x values, x equals 0, -4, and 4. Okay. Any questions on what I've done here? Okay, this is probably, I'd say, I guess it's not too bad of a question. Pretty much the same steps for any critical value question. So I think we're on the right page here. All right. If we don't have any questions, we're actually going to switch back into our packet that we started with, the max and mins packet. Let's go over this one. Okay. So back to this set of notes here. All right. This set of notes. Oh gosh, this is a big packet. Oh gosh. Oh no. Here we go. Nope. Oh my goodness. There we go. Looks like this. We talked about maximums and minimums of a graph. Basically, how high does the graph go and how low does the graph go, right? That's the absolute max and min. We also talked about local maxes and mins, and that is wherever we have a peak in our function or a valley in our function. Those are the y values of how high and low the function goes around any specific point, okay? And we did a lot of work on doing that, okay? Now we said that critical values are places that we think that there might be a local max or a local min. And we weren't actually sure when we actually found those values. Now, in the far future, we will actually be able to tell if something is a local max or a local min. But before that, we're gonna try to figure out how to do something a little bit easier. And what is easier to find is the absolute max and absolute min of any type of function, as long as it's on a closed interval, okay? So what we're gonna do is we're gonna talk about this thing called the closed interval method, okay? Whenever we are asked to find the absolute max or min of a function, that is how high it goes and how low the function goes. And it's not just a function, which means it passes the vertical line test, but it's also a continuous function. So a function that you can draw without taking your pencil off the page, right? And not just that, we also have a closed interval, okay, which just means the endpoints are going to be solid circles, okay, or brackets instead of parentheses on our first number and our last number, okay. There is a method, a step-by-step method that we can use to find the absolute maximum and the absolute minimum, okay. Now, the theory behind this is wherever the absolute maximum and absolute minimum is going to be is either going to be at the critical values where there's a local max or a local min, or at the endpoints, okay? The endpoints can also be the absolute maximum and the absolute minimum, okay? So to do this, we're going to find all the critical numbers of the function. We're also going to evaluate the function at the endpoints, and we're just going to take the largest number and the smallest number, okay? Now, I know that sounds really abstract. Let's do an actual example and actually see what's going on here, okay? So in these types of questions, I'm probably never going to ask you something too crazy. I think making you use like the chain rule and stuff like that might be a little bit too crazy for this sort of question. So let's just go over how we would do this with a polynomial, okay? In this example, we're asked to find the absolute maximum and minimum of a function. When a question asks you to do this, and it gives you a function and a closed interval, which means we're including 1 and 4, this is our hint that we have to use the closed interval method. Okay, so anything that asks you to find the absolute max or min of a function on an interval, use this method. Okay, so let's just take this step by step here. It says, I need to find the absolute max and min of a continuous function. Is my function continuous? Yeah, right, it's a polynomial, we have a continuous function. The interval is closed because we have a less than or equal to sign instead of just a left-hand sign. Let's do step number 1. Okay, step 1 says, find the values of f at the critical numbers of f in AB. Okay, maybe we should find the critical values first, right? Critical values, I guess I have to find the derivative, right? That might be a good place to start. What's the derivative of my function here? Good, 3x squared minus 6x. Okay, now critical values, first we have to find where the derivative equals 0. So we can do that. F prime of x equals 0. So 3x squared minus 6x equals 0. Any ideas on how to solve this for x? Yeah, take out an x is good, right? They both have an x. Oh, a 3x. A 3x is good, right? What am I left with on the inside? X minus 2, good. Now that we have two factors equal to 0, we can split this up into two equations. 3x equals 0 and x minus 2 equals 0. Solving these are pretty easy. We get x equals 0 and x equals 2. Okay. Now, we could do places where our function doesn't exist, but looking at this place, it doesn't actually seem like the function doesn't exist anywhere, right? We have a polynomial derivative. F prime of x does not exist nowhere. Look at that, double negative. Okay, so we don't have to think about that. All right. Now, I told you don't really have to plug in your values with polynomials, but it looks like we actually have to for the critical value method or the closed interval method, right? It says on step 1, we have to find the values of f at the critical numbers. So what we do is we have to plug in our values. So let's plug in f of 0. Now, before we go on, is step 1 telling me to plug my critical values into the derivative or into my function? The function, right? It's telling me to plug things into f, right? So plug into the original function. Just a question to think about. What would I get if I plug 0 into my derivative? You get 0, right? Because critical values are where the derivative is 0. So of course, if I plug in 0, I'm going to get 0. Okay, so that would be very interesting. Plugging in 0 to my original function gives me 0 cubed minus 3 times 0 squared plus 1, which is 1. Okay, plugging in 2 into my function gives me 2 cubed minus 3 times 2 squared plus 1. And I think that gives me negative 3. Okay. All right, let's go to step 2 real quick. Okay. Okay. Step 2 says we have to find the values of f at the endpoints. Okay. By the way, has anyone noticed that I did something a little bit weird here? All right, let's keep going. All right. It says to plug in the endpoints into my original function. My endpoints are 1 and 4. So f of 1 is 1 cubed minus 3 times 1 squared plus 1. Okay, which is, gosh, negative 1, I think. We also have f of 4, which is 4 cubed minus 3 times 4 squared plus 1, which is 17. okay? So I just plugged in all my critical values. I plugged in all my endpoints. Has anyone noticed the mistake I just made?
Yeah, it's actually -2.
Oh, is it -2? For which one?
Oh, wait, it is -1, never mind.
Okay. Ooh, okay, so I like what John said. He said we shouldn't care about a critical value that's not between the endpoints. Does everyone kind of see that? What critical value isn't between the endpoints? 0, right? I got x equals 0 here. Okay, let me highlight this real quick. And I'm interested in the absolute max and min when x is between 1 and 4. Is 0 between 1 and 4? No, right? So let me write this out real quick for your notes. 0 is not between my two endpoints, not between 1 and 4. So we don't care about 0 because it's not in the interval that we're interested in, okay? So I'm gonna take out this critical value, and I'm gonna tell you, you didn't even have to plug it in, okay? So when I plugged in 0 into my original function, this wasn't helpful to me at all, okay? You don't have to do this if you don't want to. Of course you can. It might be a little bit confusing though, okay? So I actually don't care about anything that's not in the interval 1 and 4. Okay. So my 3 candidates to be my absolute max and mins are f of 2, f of 1, and f of 4, okay? To find the absolute maxes and mins, we're gonna take a look at what these values are: -3, -1, and 17, okay? What's my absolute minimum? -3, it's the lowest of the values that I found, okay? So this is the lowest, okay? So my absolute minimum is going to be, you can write it in either way. You can either say f of 2, which is a y value, but it's expressed in terms of x, or you can say -3, okay? Now, if you were typing this into WebAssign, I would definitely prefer -3. I think WebAssign might be confused with f of 2, okay? What's my absolute max? 17, good. We can either say f of 4 or we can say 17. You cannot say x equals 4 or x equals 2 because those are x values, right? Our answer is always a y value. Okay, so we applied the closed interval method to find the absolute min and the absolute max of my function. Let's just see what this looks like on the graph, okay? So up here, I graphed my original function, x cubed minus 3x squared plus 1. And we're only interested in between x equals -1 and x equals 4, right? These are the 2 points that we're interested in, okay? Now, the reason this interval method really works is because, well, critical points are definitely things that we should look for a absolute min or maximum max, because it can be like the lowest point. But the endpoints can also be an absolute min or absolute max because, well, it can just go up to the end of the interval. Okay, so it looks like our highest point ended at an endpoint. The lowest point ended at a critical value. Looks like our other endpoint really didn't matter, but we definitely have 2 different types of mins and max going on here. Okay. Any questions on example number 16? All right. If we flip our page over, we have another question here. We have x plus 1 over x between 0.2 and 4. It looks like everyone's on the right track here. I do want to go over this a little bit more slowly, so I'm actually going to write up the answer instead of asking for a volunteer. So this equation was a little bit crazy, a little bit crazier than our polynomial. First of all, this is definitely not a continuous equation, right? So why can I even use the closed interval method for this? Okay, yeah, like the interval has something to do with it, right? This is not continuous. where is it not continuous? Yeah, at x equals 0. Okay, so why can I still do this question using the method, even though the method only applies to continuous functions?
It's not.
Yeah, right. The discontinuity, or the one place where this function isn't continuous, isn't between 0.2 and 4. Okay, so because, well, it's continuous everywhere else, even though I do have a discontinuity, we're looking at the interval where the function is continuous. So we can still do the function. Okay, so now that we know that we can actually do this, our first part of order would be to find the derivative. Now, I hate derivatives involving fractions, so I like to write the fraction in a different way. How can I write 1 over x using just no fractions? Good, x to the negative 1. Easier to work with, and we're good. All right, let's do step 1, which is finding the derivative and then plugging in those values that we're interested in. F prime of x, what's the derivative of my function here? Perfect. 1 minus x to the negative 2. Okay. Now, x to the negative 2 is what, 1 over x squared. Okay. And I put a hint here. Honestly, you could probably do this equation, or you can probably solve this without doing this. But I always like writing my derivative as a big fraction, just because I think it's easier to actually go about and do the question this way. Okay. So if I were to write this as a big fraction, I would say the common denominator would be x squared. Okay. How can I write 1 as a fraction over x squared? X squared over x squared, right? So I can just multiply the 1 by x squared over x squared. And that allows me to combine this into one big fraction over x squared. Okay. So that is my derivative. You don't have to do that step, but I like doing it. Just, I don't know, makes me feel better. All right, looks like we have to find where our derivative is equal to 0. Okay, the derivative is equal to 0 where the numerator is equal to 0. My numerator is x squared minus 1. Okay, guess we can add 1 to both sides. So x squared equals 1. Taking the square root of both sides. When I take the square root, what did I just forget? When you take the square root of both sides, what am I forgetting? Plus or minus sign, good. So x is equal to plus or minus 1. Okay, so those are candidates for critical values. Let's think about where a function doesn't exist. Well, that happens where x is, where the denominator is equal to 0, right? That's where our function is not existing. Our denominator is x squared. So taking the square root of both sides, I guess I'll remember the plus or minus sign anyway, gives us x equals 0. Okay, so it looks like we have a couple candidates for our critical values. We've got -1, +1, and 0. Okay, which ones can I throw out? -1 and 0, and why can I throw them out? Yeah, right. So I'm going to cross out -1 because that's not in the interval. And I'm also going to cross out 0 because that's also not in the interval. The only ones I care about are the numbers that are inside my interval 0.2 to 4. The other ones don't care about. Okay, so I'm just going to plug in the numbers that I am interested in. Am I plugging in my numbers into f or f prime? I'm going to plug x equals 1. What am I plugging it into? The original function or the derivative? The original function, good. The original function. We have f of 1. F of 1 is going to be 1 plus 1 over 1, which is 2. Okay, so that's one of the values that I'm interested in. Could be my absolute min, could be my absolute max. We don't know yet. Let's do step number 2. Step number 2 says take the endpoints and plug them in, right? So plug in 0.2 and regular 4, okay? Looks like we have f of 0.2, which is 0.2 plus 1 over 0.2. I'll save you the calculation here, and I'll give you 5.2 is the answer to that one, okay? You can also plug in 4, which is 4 plus 1/4, which gives you 4.25, okay? So we've plugged in 3 different things. We found f of 1, which was 2, f of 0.2, which was 5.2, and f of 4, which is 4.25. What's my absolute minimum? Not 4, 2, right? The y value 2, which you can also express as f of 1. Okay, so 2 is my absolute min. It's the smallest of all the numbers I found. What's my absolute max? Not 4. Remember, it's always the y value that we talk about. So yeah, 5.2 also is what we're looking at, right? So 5.2 is the largest number. So you can either say f of 0.2, or you can say 5.2 as our answer, okay? Can I say that 0.2 is the absolute max? No, you can't say, so you can either say 5.2 or f of 0.2. Don't say that 0.2 is the absolute max, because that's an x value. When we talk about the absolute max, we're talking about y values. So either f of 0.2 or 5.2. Don't say 0.2. Okay. Any questions on example number 17? All right, then I guess I don't really have anything else for you guys today. Have a very happy Halloween. You can have fun, but don't have too much fun. And I will see you on Wednesday.